and share. Okay, so GNG 100, and today is March 3rd, 2021, and the plan of today is to continue the joint probability distribution and in particular we will do the covariance. Okay, so let's kind of review, since we started this topic a while ago. We defined joint distributions as f of x and y is just the probability that random variable x takes value x and random variable y takes value y, and we said that f of x, y, if we sum over x and over y, it should give us 1, and f of x and y is greater than or equal to 0. And we defined also marginal probabilities. This is the joint BDF, and then we define the marginal BDFs as, if I'm interested in f of x, then I will sum over y, and if we are interested in y, we just sum over x. So this is for the discrete case. For the continuous case, f of x and y, we do not define it in the same way. The way we define it the continuous way, I don't define f of x and y to be equal something like we did here, but the way we do it is we define the volume under f of x and y, and this volume should be 1 for this to be a valid joint distribution. So, Professor, will you announce midterm for the students who did not do the exam? Did you do the exam? Hussein, you did the exam yourself, right? Don't worry about the others. You did not do the exam? خلاص. Once you do your exam, I will announce your grade. Yes. For those who have medical excuses or quarantine, I'll wait until everyone finishes the quarantine, and then I'll group them all in one exam. This might happen before the break, might happen after the break, I don't know. But I will not do multiple exams, so we'll find a suitable time for everyone. Okay, and then to do the marginal, and it will be a different exam. I will announce this grades to the students, yes, because it will be a different exam for those who did not come. So to the marginal, we integrate over the other one, and to find f of y, we integrate over x. We also did conditional probability. We said f of x given y is just the joint over the marginal. And finally, we did independence. And independence, we said that f of x and y is just f of x times f of y, which means that the joint equals the product of marginals. So this is the most popular condition for independence. Majid, you have a question?
Doctor, what if the product has a small difference? Is that still not independent? Because in the exam, the same question came, but there's only a little difference. Is that then?
If this little difference is due to your, and usually what we do here, we do the on the PDF level. So the equation, it will be an equation. So the equation should not have any difference. If we are dealing with discrete random variables, it should be exactly the same. If the difference is due to your rounding, then you should not round. You should keep it as like ratios. You should not round. So it should be exactly the same. Okay? Of course,
Okay, makes sense.
There are other conditions that, of course, you can use, or f of x given y is just the same as f of x. So what are we going to do today is, how do we characterize relations. Don't know what's going on around me. Somebody is drilling. How do we characterize relations between random variables? This is what, if they are not independent. That's noisy. Covariance. And covariance is just a tool or a metric. Let me say it's better than a tool. A metric to measure the relation between two random variables. Let's say two random variables. And for us to understand the covariance, we need to understand the expected. I will define it very shortly, but we need first to understand the expected value of a function of two random variables. So remember, how did we define the expectation of, for a single random variable, expectation of x? It was just x f of x, right? Dx. What was expected value of x squared? Again, integration of x squared f of x dx. What was the expected value of any function of random variable? It's exactly that function multiplied by the PDF, and then integration or summation if we are dealing with discrete random variables. So similarly, for two random variables, expected value of h of x and y is double integration h of x and y f of x and y dx dy for continuous, or double summation h of x and y, f of x and y, dx, dy for discrete. Let's do an example. I think such definitions are clear only if we do an example. So let's do an example. So given the following f of x and y, where I have something like this. I have x here, where x can be 1 or 2 or 3, and y can be 1 or 2 or 3. This is y. And let's assume I have a probability of 0.2 here, a probability of 0.2 here, and a probability of 0.3 here, and then a probability of 0.1 here, and a probability of 0.2 here. And then is this a valid? Is this valid?
No, doctor, because it's not a triangle.
It should have a
Why is not valid?
Rectangle.
shape.
All of
Have.
it. It's
The
not
point
valid because
should-
one of the
should
points is not
have a
given.
rectangular shape.
Any joint distribution should have a rectangular shape. I did not say that.
Yes.
You understood that. That's
No,
your problem, but I did not say that.
It's valid but not independent.
Yes, I'm not asking about independent. I'm just telling, is this valid? Yes, you're right. This cannot be independent. X and Y in this case cannot be independent. But I'm asking a different thing. I'm asking, is this a valid probability distribution?
Yes, valid.
It should be valid, right? Why? Because
I think we should find the sum in the beginning.
f of x is greater than 0. All of them, we see 0.1, 0.2, all of them are positive. And the summation, if you sum them, 0.1 plus 0.2, 0.3, 0.5, 0.7, 1. So yes, so valid. Then if I tell you find expected value of h of x and y, where h of x and y equals x minus mu x times y minus mu y. This is my function. So I want you to find expected value of x minus mu x, y minus mu y. According to the definition, I should use this double summation to do it. So I need mu x and mu y. These are constants. I don't have them. So let's see. Let's find the marginal. Let's find x and y and their means. So let's do x first. We said the way to do the marginal, we sum those. So summation of those are 0.3 here and 0.7, right? So what's my f of x? X can be 1 or 3. What's the probability of 1?
0.2,
0.3. And what's the probability of 3 is
0.7.
0.7, right? So what's mu x? Mu x, we know that's summation x, f of x, which is you take each value and multiply it by its probability. So which is 0.3 plus 2.1, which is 2.4, right?
Yes, doctor.
Okay, so I'm waiting for your confirmation to continue. Thank you. Just kidding. Okay. Then to do y, we sum horizontally. So y can be 1 or 2 or 3. with probabilities. So if you sum this is 0.3, this is 0.4, and this is 0.3, right? So what's y? Y, f of y. So y can be 1, 2, 3 with probability 0.3, 0.4, 0.3, right? This is what we got from the joint distribution. So what's mu y? Mu y is y f of y, which is 1 times 0.3 plus 2 times 0.4 plus 3 times 0.3, which is 0.3 plus 0.8 plus 0.9, 17.2. So this is simply 2. So now I need to calculate expected value of x minus mu x, so x minus 2.4, y minus 2, which is double summation using the above equation of x minus 2.4, y minus 2, f of x, and y. So I go up. Let me just repeat the joint, or let me first go back to our color. Let me draw x and y again. So I have 1, 2, 3, 1, 2, and 3, and then I have 0.1, I have 0.2, and then 0.2, 0.2, and 0.3. So I need to do for each probability point, I need to calculate this. So let's find this out. So first, I take x1 and y1. What's the probability at this point? So when x1, so 1 minus 2.4 times 1 minus 2 times the probability is 0.1 plus. Let's move to the second point. At this point, x is 1 and y is 2. So 1 minus 2.4, 2 minus 2 times 0.2. Do you see what I'm doing? I'm going each probability point. So if I have like a new color, I do each point. I see what's the corresponding value of x and y. I use them in the equation. So let's do the third point using this color. So let's do this point. So what's x here? X is 3 and y is 1. So this is 3 minus 2.4. Y is 1 minus 2, and the probability is 0.2 plus. Let's do red. So let's do this point. At this point, x is 3 and y is 2. So 3 minus 2.4, 2 minus 2, and the probability is 0.2. Finally, let's do whatever, this one. So this point. So at this point, x is 3 minus 2.4, and y is 3 minus 2, and the probability is 0.3. Yes?
Why did you do the x-axis first, yani axis by axis? Why didn't you do the y-axis?
It does not matter. You start. The important thing is to cover all of them. Okay?
Tamam.
So it does not matter what way to go. You need to cover all of them. So if you do this, if you calculate all of this, you will find out that this is 0.2, which, as we will see, this will tell us about how strong is the relation between x and y. So given x and y random variables, the covariance of x and y, which is denoted as covariance of x and y is equal to sigma xy is just, let me, so covariance is defined as, so covariance of x and y is some sigma xy, which is the expected value of x minus mu x times y minus mu y, and you can show that this is can be done in a simpler way, which is xy minus mu x y, or this way. So it can be written in like this. So in the same example, in the above example, if I give you that joint distribution and I will ask you to calculate what's sigma xy, it's simply expected value of xy minus mu x mu y. So you could have done it in an easier way, which is some double summation xy f of x and y minus mu x mu y, which is just come to each probability point and multiply the values 1 times 1 times 0.1, 2 times 2 times whatever. So it's, you could have done it in a similar way, which is 1 times, when x is 1, y is 1, and their probability is 0.1, plus when x is 1, y is 2, and their probability is 0.2, plus when x is 3, y is 1, the probability is 0.2, plus when x is 3, y is 2, the probability is 0.2. When x is 3, y is, and probability 3, 2.2, 3, 1, 2, 3, 4, 5. So this is 3.3, and then minus mu x mu y, which we know to be 2.4 times 2. And if you do this, you will get exactly 0.2. So what we are saying is that this is number tells me about the relation between x and y. So what does it mean? So what does this mean? So covariance mean is a measure of the linear relation between two random variables. Okay? So if the covariance is positive, it means that x and y are either large together or small together. So they have this kind of relation. If x is large, then y is large. When x is small, then y is small. If this number was positive. So in this case, yes. However, if sigma xy is negative, it means when x is large, then y is small, and vice versa. When x is small, y is large. So if I give you a joint distribution like this, I'm telling you this is x and y, so I give you something like this. As you can see, there's a trend like this, right? So when x is large, y is large. So this is positive covariance. Without calculation, we know that sigma xy is greater than 0. However, if the shape of the joint distribution was something like this, something like this. So as you can see, when y is large, x is small. When x is large, y is small. So in this case, we have negative covariance, and sigma xy is, if you calculate it for this specific scenario, you will find out that the covariance is negative. So what if we have something like this? What if we have like equal probabilities like this? Or like I have a circle and then I have equal probabilities just around the circle. So in those cases,
0.
there is no linear relations. Yes, so covariance is 0. طيب. The question that might come to mind now. So in the above example, is point 2 a strong relation or a weak relation? And why I'm saying this is because sigma xy can be 0.01, 0.1, 1000, negative 5000. It can be any number. There is no real way to tell. There is no real way to tell whether it's a small or. So we need what we call. We need a kind of normalization. We need a normalized version of covariance. Like, for example, grading exams. We grade exams out of 100 or out of 10. Because you can't go back home and your dad tells you, how did you do in the exam? You can't say, oh, I got 90, and the exam was out of 500. It does not make sense, right? So we need a certain normalization so that when you tell the value to someone, they will know whether it's wrong or not. So we need some kind of normalization, and this is why we define correlation. So what's correlation? For random variables, x and y, correlation is defined as rho xy is covariance of x and y, and then we divide by the square root of the variance of x, variance of y, and so we can write this as sigma xy over sigma x sigma y. And you can show, we can show that rho xy is bounded between 1 and minus 1, because covariance of x and y cannot be stronger than sigma x times sigma y. This is the ultimate, because they are independent, it will be sigma x, no, sigma xy will be 0. But if I'm doing OXX, so sigma xx is just sigma x squared, then it will be sigma x squared over sigma x squared, so it will be 1. So if rho xy is close to 1, positive 1, this means strong positive linear relation. And if it is close to -1, then strong negative linear relation. And if rho is close to 0, then weak linear. Okay, so again, if we go to the above example, for the above example, what is rho xy? Rho xy, we know that it's 0.2 sigma xy over sigma x sigma y, right? We calculated sigma xy, it's 0.2 over sigma x sigma y. We don't have sigma x sigma y, we can calculate sigma, the variance, we can calculate it as, we know the equation, x squared f of x minus ux squared. Seems that the guy was resting and then he's back to his drill. So it's so this is 1 squared times 0.3 plus 3 squared times 0.7 minus 2.4 squared. So you can calculate sigma x squared and then you find sigma x, and sigma y squared similarly it will be, I'll just write it for you if you want to check it later on, plus 2 squared times 0.4 plus 3 squared times 0.3 minus 2 squared. So you can calculate sigma x and sigma y, and then rho xy will be 0.2 divided by that product. If that number is close to 1, it means it's a strong relation. If it's close to 0, then it means it's a weak relation. Type. Let me do another example. If we have a square joint PDF. Let's see, is the covariance 0 or not? So if this was my x, this was my y, let's assume that I have 1, 2, 1, 2, and I have 4 points. So let's say this is 0.4, this is 0.1, this is 0.4, this is 0.1. What do you think? This will be 0 or positive or negative correlation?
0, doctor.
Okay, let's see. I don't know. I don't think so, but let's see. Covariance xy is whatever summation xy minus mu x mu y, right? Again, what's mu x?
The mean, doctor.
Yes, the mean. So the mean of x, 0.5
1
times
times
1, 0.5 plus 2 times 0.5, right? Which is what? 1.5. Mean of y?
0.5 times 1
1.
plus 0.5 times
Again,
2.
The same.
which is 1.5. So let's calculate the covariance. So sigma xy. So again, we'll multiply 1 times 1 times 0.4 plus 2 times 1 times 0.1 plus, okay, I have 10% in mind and I don't have the charger with me. Inshallah, we'll be able to finish. 2 times 1 and then 1 times 2 times 0.1 plus 2 times 2 times 0.4 minus mu x mu y, so 1.5, 1.5. So let's see. So this is 0.4 plus 2 times 0.1, 0.2 plus 2 times 0.1 is 0.2 plus 4 times 0.4 is 1.6 minus 15 times 15 is what? 625? 1 second, Majid. 15 times 15 is 1.5 times 1.5, 225. So this is 0.4, 0.8, 2.4 minus 2.25, which is 0.15. So it's not zero. Majid, you have a question?
Yes, first, you're right. So it's not 0 because I think from 0.4 to 0.4, it's increasing for both of them. And 0.1 and 0.1, it's lesser. It's less than that, the upward trend, I think.
Yes.
So hence why it's positive. The question here, doctor, is for the variance xy. It's 1 times 1 times 0.4. What exactly are we doing here? If you could please remind me again. I'm lost. Sorry.
You mean here?
Yes, yes.
I'm just applying the relation of the covariance. What's the relation of the covariance? Covariance was defined as
Py
x times y times the joint. Yeah.
Got it. Yes. fxy. Yeah. Okay. Perfect. Yeah. Perfect. Doctor.
Okay.
Thank you so much.
So we just applied it here. So again, yes, exactly what you said. Since these are not equal, so you see, you have more probability that x and y will be large together, which is 2, or small together as 1, and less probability that x is large and y is small. So it's positive covariance due to larger probability for 2, 2, and 1, and 1. Try it yourself. I will not do it. Try. XY, where you have 0.25, 0.25, 0.25, 0.25. This will give you.
For sure. For
0.
sure.
Okay. I think we can take the attendance and then we continue. I'm lucky in the morning. I have Sijoy with me. He helps me in the. So now I need to log into Blackboard again, and this, Blackboard is very secure now for us. You need to receive for some reason. I don't know who's going to hack Blackboard. Anybody interested, you think, in hacking our Blackboard, Qatar University? Don't think
Yes,
so.
doctor. To fix the attendance for everyone.
No, I would not pay 10 riyals for anyone to fix my attendance. Anyhow. So where's attendance now? I can see maybe somebody hacked. Okay, yes. I can see. Okay, I will enable. Please log into your Blackboard and mark your attendance. We'll pause for like 1 or 2 minutes to give you time to check your attendance.
Doctor, will you upload the solved for the midterm solved sample, if possible?
The one that you I gave to you?
Yeah, the midterm
Solution,
that
you
you
mean?
yeah, if possible for you.
Yeah. I will post the solution. Yes, for sure.
Sorry, doctor, one last question.
Sure.
The final exam,
I'll
will it
stop
be like
sharing. Yeah. You are asking about for the final exam. Wow.
yeah,
Okay.
will it be cumulative or will it be like most of stuff after the midterm?
It's comprehensive. Yeah. It's comprehensive. Yeah. Focus more on the second. Usually in the final, I give 5 questions. Usually 3 questions from the part after the midterm, and then 2 from the one before. That's at least what I used to do in the past. But see how much, because they cut the semester by one week, so I'm not sure what how much we can finish after we come back. So we'll see. طيب. Note, important note. If x, y are independent, then for sure sigma x, y will be 0. So if you tell me that x and y are independent, I will know for sure that they will have no covariance, or covariance is 0. Why? This is simply because independence means that x and y have no relation whatsoever, linear or non-linear. And we know covariance is just characterizing the linear relation between x and y. And that's why, however, if sigma xy x is 0, which is the same as rho xy is 0, will x and y be independent? So if I tell you that rho xy is 0, so x and y, they have no linear relation, does that mean they are independent? The answer is not necessarily, no. Because rho xy equals 0 means no linear relation. But they might be related in a nonlinear way. So, independence means uncorrelated. However, are uncorrelated, then not necessarily independent. Yes, question?
Doctor, my question is regarding, you said if we have the rectangle and one of the points is not given, one of the probabilities is not given, why is it for
What's that?
surely when you
Can you
have
repeat?
when you have the joint distribution, right, and you have this rectangle with the different dots of the probabilities, if one of them is not given, you say that it's not independent, right?
Yes.
But on what basis though? Like,
If it's missing, if it's not rectangular shape, then for sure they are not independent.
no, what if there does lie a probability, but it's just that we are not given? Like, how are we sure it's not independent?
What do you mean? There's a probability and it's not given.
You mean, so if you have a rectangle and one of the points is not given, you say for sure it's not independent, right? But what I'm saying is, what if that probability exists, but it's just that we are not given? Why
Yeah,
don't
but
we
there's
just say,
what matters is if there's a probability or not. What does not matter whether you know it or you don't know it. That does not change the structure of the random variable, right? You knowing it or not knowing it does not change the structure of the variable. If there exists a probability regardless of how small it is, then if you have a rectangular shape, this is an indication that they might be independent, not necessarily independent. We said if there is a missing point, for sure they are not independent. But if it's a complete rectangle, then you need to calculate the conditions and see if they are independent or not. So
okay,
using just the shape, we can prove they are dependent. So we can prove dependence, but we cannot prove independence. Okay?
yep, that's clear, yeah.
Okay. Okay. Note number 2, only for Gaussian random variables, independence and correlation or uncorrelation are equivalent. So if x and y independent, if x and y Gaussian, then if x and y are uncorrelated, well, let me just write a shorthand. Then if rho xy equals 0, this means that x and y are independent. Only for Gaussian random variables. For any other random variable, this is not the case. Okay, so let's do probably the last topic that we want to cover in this chapter, which is linear functions of random variables. What's a linear function of random variables? Define it this way. If x1, x2, x3, all the way to xp are random variables, then y equals c1 x1 plus c2 x2 all the way to cp xp, where c1, c2, cp are constants, is called a combination of x1, x2. So we'll continue until it dies. XP. I have 5%.
I'm betting on it, doctor.
And okay. I brought with me, because I'm in a different location now, I brought with me the wrong charger. After arriving, I found out that because USB-C for the iPad looks very close to that of the Samsung. Okay, so we call this a linear combination of random variables. So what is expected value of y? Expected value of y. Majd, let me finish. I'm afraid that I will not continue. I'll please keep the questions till the end. So it's c1 x1 plus c2 x2 all the way cp xp. Then you can take the constants outside. Plus cp, expected value of xp, which is c1 mu1 plus c2 mu2 plus cp mu p mu xp, sorry, mu x1 mu x2 mu xp, and the variance of y will be the variance of, again, the linear combination, and which is, will be interested only in the cases that the x's are independent. So it will be variance of x1 plus c2 squared variance of x2 all the way plus cp squared variance of xb for x1, x2 all the way to xb independent. So the x's are independent, then the variance of their linear combination is just their variances added together and scaled by the squares of the constants that are that are given in the linear combination of them. And we also can define the average of p random variables, which is defined as, and we will be dealing with x bar substantially in the next part of the course. If you define x bar like this, where x1, x2, xp are identical and independent random variables, so all have mean, mu, and variance sigma square. So if I have x1, x2 all the way to xp, they all have the same mean and the same variance. And then I define x bar to be x1 plus x2 all the way to xp. And I ask you, what's the expected value of x bar? We use the same relation that we did above. So this is, you take the constant outside. So this will be mu plus, because all of them, they have the same mean. So it will be 1 over p times p mu, which is mu. So if you are taking the average of 10 random variables who have the same mean, then the mean of the average is the same as the mean of each one of them. However, if you do the variance of x bar, and then applying again the same relation, so it will be the variance of 1 over b x1 plus the variance of 1 over b x2 all the way plus the variance of 1 over b xp. So using the same relation, so this will be 1 over p square sigma square plus 1 over p square sigma, because all they have the same variance, and 1 over p square sigma square. And how many I have? I have p of them. So if you add them all together, it will be p over p square sigma squared, which is sigma square over p, which is a very, very important relation that we need to get back to it when we talk about statistics, because as you can see, the variance of x bar is sigma square over b. So if b is large, I'm taking the average of very large number of identical random variables. When b goes large, we see that the variance will go to 0, right? If b is very large, then the variance of x bar will be sigma square over very large number, which will tend to 0, and we will be in a better position to understand why is this the case when we talk about estimation, because this x bar is a very important estimator that we will be dealing with later on. The last point I want to cover is the reproductive property, which is a property of normal distributions. And simply it says, if you add or subtract normal random variables, you will get another random variables. So if x1, x2, all the way to xp are independent, normal or Gaussian random variables with means mu I, so each one has its own mean, variances sigma I square, then I, which is c1 x1 plus c2 x2 plus cp xp, is also normal, also normally distributed with the mean of y is just according to the relation that we did, c1 mu x1 plus c2 mu x2. No, I call it mu1 and mu2, sorry. In this case, it's just, I call them mu I. So c1 mu1 plus c2 mu2 all the way to cp mu-p. And the variance of y is c1 squared sigma 1 squared plus c2 squared sigma 2 squared plus cb squared sigma p squared. So the reproductive property of normal distribution is very important property. Again, it simply says that if you add scaled versions of normal distribution, then the summation will give you another normal. How to calculate the mean of the new normal distribution is just multiply the constants by the means of the corresponding individual random variables, and you can calculate the variance exactly the same. So all of what we have covered is based on the very original linear functions of random variables, the way we deal with linear functions of variables. And based on these relations, we can, and I can give you questions like, for example, we can do, let's try to do this example. Sorry, I can take your answer because I have also my laptop. My laptop has power, so I can talk to you verbally, but I cannot write. So let's do a quick example. How about if you put two sheets on top of each other, and you know that the width of sheet 1 is x and the width of sheet 2 is y. So width of sheet 1 is x, width of sheet 2 is y, and we know that x and y, they are not perfect. We know that they are normally distributed with mean of 2 and variance of 0.1. So those who manufacture those sheets, they will not be exactly, each one of them has a width of 2 millimeters. We know that it should be 2 millimeters, but it might be a little bit less, little bit more. So it's normally distributed with mean mu, mean of 2 and variance of 0.1, of 0.01, sorry. So what's the distribution of the total width? Distribution of total width, t, let's say t. So t is what? T is simply x plus y, right? The total width is x plus y. So x plus y follows which distribution? N1 normal, right? X and y should be normal because I'm adding two normally distributed random variables. So this is normal. What's the mean of this distribution? The mean is just mu x plus mu y. What's the variance? Variance is just sigma x squared plus sigma y squared. So t is normally distributed with mean of 4 millimeters and variance of 0.02 millimeters. And now I can ask you, what's the probability that the total width is greater than, what's the probability that t is greater than 4.2, for example, millimeters? When you put those together, you are concerned that you will be stacking some of those sheets on top of each other. So what will be the probability that the total width will not fit in the location that you want to put it in? So you can calculate this probability again using the table, using the standardization. This is the probability that t minus mu over sigma is greater than 4.2 minus 4 over square root of 0.02, and you can go to the table, and of course it's better than z less than 0.2 over square root of 0.02. So you can do this from the table. Okay, questions? I think I managed to cover quickly what I wanted to cover. If you have questions, I can answer the questions now. No questions. Okay, so if you don't have any questions, then I think that's I can stop the lecture here. What's important for today is that we cover the covariance. It's a metric that we use to quantify the linear relation between two random variables, and we learned how to calculate it. We learned that for normal distributions, correlation and independence they mean the same. So if you tell me they are uncorrelated, I will know exactly that they are independent. If you tell me they are independent, then like any other random variable, they are uncorrelated. And we talked about linear combination of random variables and calculate the mean and the variance of the linear combination of random variables. And more importantly, for normal distribution, we know it's reproduce itself. So if you add normals to each other, it will give you exactly a normal distribution. And we mentioned this theory before, the central limit theorem, that tells us even if we add any other random variables, but with large numbers, it will also give me normals. So yani, for sure, if I add normals, it will give me normal, because we know that adding large number of different random variables will give us also a normal distribution, approximately. But for normals, adding normals together will give you exactly another normal distribution. Mixture of different distributions will also give you normal if they are large in number. This is the sense of the central limit theorem that we mentioned briefly, and we'll talk about it at one point in this course. My iPad is really well. It still have 2%, so you can see it. I think it's in the upper right corner. It's 2%, so the iPad is perfect. And yeah, so anyone, any questions?
Doctor, this is an amazing tool. So basically, we can also make stacks, like we can check the mean and variance for 10, and then maybe you can calculate for hundreds of them. The question here is, can you give any more examples of this same logic being applied to some other real life examples?
About what? About
to use the same concept to calculate like two different normal distributions, and then finding, like, you know how you did over here to check what is the probability that the total combination of the two tiles or two sheets will be this much. Do you have any other examples we normally use in real life?
Let me try to think. And this kind of thing, they usually use it when if you have parts in the cars, any parts that you need to fit with each other. If you have screws and then they need to fit in certain holes, then you can always calculate if both are normally distributed, the width of the screw that should go into the hole, then you want for sure the diameter will not be larger than you can always calculate if both are normal. What's the probability that one normal is larger, which is much harder problem, by the way. What's the probability that one normal distribution is larger than the other normal distribution? So this is a very difficult problem, but adding them, what's the probability that nothing comes to my mind, actually, sorry for right away. But this kind of probabilities, again, and in my field, we just use it. Noise is the most famous example that we use the Gaussian distribution in, and we use it to model many other things. The most recent problem that I was dealing with is like in starting 4G and 5G systems. They use a certain communication scheme, which is called OFDM, or orthogonal frequency division multiplexing. Those, in this case, you should have orthogonal carriers, orthogonal frequencies, and due to the wireless channel, it's always the case that they are not perfect, and you will have interference between the carriers, and this interference is modeled as a Gaussian distribution. And believe it or not, in this case, the approximation is not that good. We just one paper was published that in certain ranges or in certain powers, this approximation using the Gaussian distribution is not good enough. Why it's not good enough? Because we do not have large number of them. So in OFDM systems, you are dealing with number of subcarriers. It might be 256, it might be 512. This is the maximum number, and the Gaussian approximation usually is valid for larger number of random variables. So yeah, it's depends on on the field that these examples that we give in the class is very trivial examples, but Gaussian assumption and Gaussian approximations are really important tools in research in many fields, not only in communication. Chemical engineering related, I think most chemical engineering you deal with processes, and all processes they have some kind of noise. You design your system to whatever boilers and all kinds of processes that you do. It will not function perfectly the way you designed. If you put certain pressure and certain temperature, you will get certain amount at the output. It's not always the case. You will always, the amount is not exactly the same amount that you designed to. So there's always an error in the output, and in many occasions it's modeled as a normal distribution. So normal distribution will live with you if you are interested in research, or if you are interested in knowing more about random phenomena that accompany different processes that you face, mainly in your professional career, not in our daily life. In our daily life, you will see the grade, and I expect the distribution of your midterm, since we have like 70 plus students taking the same exam. If we put if we plot the histogram of the grades, I expect it to be a normal distribution. I will not force it to be a normal distribution, but I expect it to be a normal distribution. Okay, mashallah, 2% still. طيب, thank you all, and I wish you a very nice weekend, and we'll talk again on Monday, inshallah.
Doctor, it's like the reserve. It's like the reserve fuel of the car. The last line, it goes till infinity.
Yeah, this is the tail of the Gaussian. So it's sometimes it's good. Okay.
جزاك الله خير.
دكتور
حياكم الله. أهلين. Any questions?
دكتور بالنسبة للأنسر كي حق